let's move on to our next speaker, and that's Ron McNaughton, and he'll do part two of Weighing the Earth 2.5 centuries ago. Go ahead, Ron.
Hello, everybody. Last month, I talked about the astronomical observations for weighing the Earth, and there's a whole bunch more things to go. And I'm going to go a brief review for the people that missed last month's meeting. Newton did see an apple fall and was stimulated to think about the moon and how it went around the Earth from that. And with relatively little evidence, he proposed the universal law of gravitation in his book Principia, that there's a force between any two masses and it's proportional to the product of the masses divided by the square of the distance between them. One corollary of that is if you have two objects like the Earth and Jupiter with a satellite, from the periods of the satellites and the distance, you can work out how much one is heavier than another. So this diagram's to scale, by the way, with planets and distances. So Newton knew that the moon was that distance away in about 27-day period compared to stars, and the values for Jupiter were found later. And from that, boom, you know that Jupiter's about 300 times heavier than Earth. But nobody knew the mass nor density of Earth. The surface dense rocks were about 2.5 times water density. The whole Earth, who knows? Newton wondered if a mountain could deflect a plumb line, but didn't think it could be measured. But Neville Maskelyne thought it could be. So at age 28, he went to St. Helena Island for a good view of clouds during the transit of Venus. He also used a special telescope to find parallax of Sirius, seeing if that bright star is close, and it might move a little bit compared to more distant stars over the year. And there was a problem with it that he ended up figuring out and explaining what the problem is, produced a solution, and maybe because of that, at the tender age of 33, he became Astronomer Royal. And that was a powerful position. He supervised a new book that gave data for mariners. He organized the transits of Venus expeditions in 1679. And in 1772, he proposed the experiment that I'll be talking about. They searched Britain and they wanted a mountain that was tall, isolated, had a ridge roughly north-south, and they ended up with one in the center of Scotland. The idea is if the mountain deflects a plumb line, if you use a telescope compared to the plumb line and study the stars above, you might detect an effect. So they had one station on the south side of the mountain and another on the north side. And these are pictures by Boyd Harris, a retired civil engineer. And he showed Neville started in the south side and then he went to the north side. He used a zenith sector telescope that only looks straight up. So there's little atmosphere, as Chris was talking about, to disturb any observations. The guy, when the timing was right to see a star come, he looked through the telescope. This candle went through a hole in the tube and reflected down to illuminate crosshairs. And he observed exactly where the star passed from the east side of the sky to the west side of the sky when it's highest. This diagram does not show the plumb line that was critical for measuring too. Maskelyne used a different one, and believe it or not, there's no sketch nor any sign of this instrument, even though it was historically important. So now I have a third important sector that still exists. This is a picture of it here hanging on a wall. And it was built in 1727. Improvements, various improvements, and good sketches were made of it because it was going to South Africa, and if it got damaged, I guess they wanted to make another one. The key is they have the plumb line that goes all the way from top to bottom. And my guess is the artist didn't show, but they might even had a piece of wood to cover it to prevent winds from disrupting things. Look through this microscope at a gold dot behind the silver wire, and you tweeted the micrometer. And then you look through the optical, the eyepiece, and you measured how many twists of the micrometer were needed to get it to exactly where the star was. Around arc second accuracy, incredible for 250 years ago. When it's near a wall, it just sits there. But when it's used in the field, they made a structure similar to this. Notice there's a dual structure because for every observation, the astronomer had to climb up to do a measurement up here, and you didn't want to have any weight on this. So this part fit exactly here. And after a whole bunch of observations in July on a very rainy year, Maskelyne then turned the whole instrument 180 degrees. So instead of the optical tube being this side, then it was on the other side, and he measured all over again in case there were any inaccuracies in the alignment of the pivots and everything. So that made it more accurate. Then, after many observations in August, they packed it up, carried it up over the mountain, back down the other side, and set it up, and he spent another 2 months observing. Wow. 337 observations. And the difference in star positions with all sorts of averaging was 54.6 arc seconds. Now, I was asked a question, and I didn't give it as good an answer as I wanted to. So I just want to talk about aberration and notation. Maskelyne's paper said, notice the S's are written as F's, but sometimes F's are real F's. Anyway, after making proper allowance for precession, aberration and deviation and semi-annual solar notation of Earth's axis, and then see his tables. Now, I didn't look up the tables, but I'm going to explain precession and semi-annual solar notation. I have no idea what deviation is, and then I'm going to explain aberration, which are all interesting things that I didn't really understand. Spinning tops, when they start tilting, they tend to go around in a circle with the bottom on the ground. Now, the Earth is not perfectly spherical. It's bulged a bit in the equator, and if the sun is at this horizontal level, it gives a slight tug on it, and it causes the direction that our axis points to change over 2,000 or 26,000 years, and that's called precession. There's also a smaller cycle with motions caused by the changing patterns of the moon's orbit, and that's about 20 arc seconds. Now, I don't quite know why, but the Saros cycle for eclipses is 18 years and just a few days, but this other cycle is 18.6 years. Now, there's one more cycle, the semi-annual, and that is the sun moves faster in January, or the Earth moves faster in January than it does in July, and that different speed has a tiny effect, and that was also adjusted. I never understood aberration of light until I was researching this paper. If someone's standing in a calm day when it rains, the rain goes straight down. So the umbrella works. But if somebody is walking or running, the rain seems to come toward them. Now, if you take a picture from inside a restaurant window of somebody running past in the rain with an umbrella, the rain still looks like it comes straight down. But if you have a camera that moves with the runner or the fast walker, you'll see that the rain tilts a little bit. And that might be if you're making a movie at the end of a romantic comedy where there's the compulsory chase scene, and et cetera, et cetera. Now, aberration is caused because the Earth moves at about 30 kilometers a second. And James Bradley used the instrument that I showed pictures of to figure this out. And he knew it moved 30 kilometers a second. And he measured an angle of 26 or 20 arc seconds where a star that is perpendicular to the solar plane, and that would be about halfway between Vega and Polaris, and it would seem to make a circle along with the other stars in the area that was picked up by the instrument. From that, he was able to work out that the speed of light was about 300,000 kilometers a second, and he was quite accurate. So this was very important for Maskelyne to do because he started in early July and it was about a third of the Earth's orbit to the end of October for his finished observations. And definitely this would affect the result. And supposedly he corrected for everything. Okay, now the survey. Theodolites are instruments, or I've heard them also called construction transits, where you can change the angle and accurately measure after leveling it, and you can also change the elevation and accurately measure that. For distance, they used Gunter's chain plus something else I'll explain later. I want to go back to the first estimate of the size of the Earth by Eratosthenes, and he supposedly, his book was lost, but somebody else talked about it. There was a well in South Egypt that was light shone straight into on solstice day. And in Alexandria, there was a 7.2 degree angle. And doing some multiplication, he figured out what the circumference and eventually the radius of the Earth was. But I'm interested in how he found 5,000 stadia. They had professional pacers that actually could get distances within a percent of modern measured values on the distance on a road. Maybe he had a professional pacer measure it, or he worked in a library in Alexandria and maybe he could gain documents of all the surveys of the whole Nile Valley, which must have been well surveyed to get that. But my point is that any astronomical measurement of distance has to go back to some human scale measurement by some way. Most of Canada long distance was surveyed by triangulation, and it's done up until the 1980s when satellite techniques ended up being more accurate. So you pick a baseline that's very accurate, and then you measure various angles from there, and you set theodolites on mountains or towers on mountains, such as this one near Georgian Bay. So the theodolite sat on this tower at 73 feet. Now you can't take astrophotos when you walk on a deck. So there was a separate support for the astronomers or the surveyors, and the tower went up to 150 feet, and they would put a lamp there, and you could see all the way from Lindsay to Georgian Bay. The length of the baseline, they actually used wooden poles that had metal on the end, but later surveyors found they weren't accurate, and they used Gunter's chain. And here's a picture from in New Mexico where they're making a baseline, and they have some structure that supports the chain all the way through, protects it from the sun. They measure the temperature, and they count how many times a chain is used because it slowly gets bigger, and somebody worked out a pattern there. This is well done. And I read in India for the survey there, George Everest, the head of the survey department, asked for the lengths to be done by 3 different groups that didn't talk to each other to be more accurate with it, because the whole thing depends on accuracy. What about bearing? Well, Polaris goes in a circle around the North Celestial Pole, and now it's 44 arc minutes or 3/4 of a degree, but back then it was almost 2 degrees, and this is the precession effect over 26,000 years. And they're books with tables for each year that give the timing and distance they are in east or above or left or west or whatever. And here's an example of a survey done about 5 kilometers for our cottage at Christmas Day in 1861 that my brother Peter discovered. And at 14 minutes to 1, they have the different angles and all the formulas and everything there. So you have your baseline. Then from each, they start measuring angles to different spots. And you get a series of triangles, and you end up with a survey all the way around. And the 2 observing sites were this red dot and that red dot. Then you wanted the size of the mountain for the calculation. So they used the altitude structure, and they ended up using 2 theodolites. So one would be here, and it would measure the angles, and there would be some signal to tell somebody carrying a pole to move left or right, etc. And then there'd be another theodolite that would then measure the bearing to there, and you're able with those two measurements to quickly find lines, and that's why they're all lines through there. I'm just trying to show you the background here of the incredible amount of information that was measured and had to be processed by Charles Hutton, a mathematician. And remember, each multiplication required hand conversions to logarithms, and then add the logarithms and then anti-logs, and just the hours that he had to spend just calculating. He found the north-south distance was 4,364 feet from all these stations. Now, there was an argument about the shape of the Earth in the early 1700s. Some felt the polar axis was bigger, so it was shaped like a rugby ball. And other people thought probably the equator bulged out, including Newton, and I've grossly exaggerated the amount of bulge. So they sent a group to Lapland, and in a few months, they measured the length of a degree of latitude. They sent another group to Peru, and that was a yellow picture I showed you. And it took them a few years to measure a year of latitude. But there's a pattern that latitude gets longer as you get closer to the poles. And somebody worked out a formula, and they used that formula to say at the latitude of Schiehallion, or the town of Pitlochry that's nearby, 101.64 feet is 1 arcsecond. So you divided the distance by that, and you got 42.94 arcseconds of latitude. And then the second big step in the calculation, you take your astronomy angle, subtract that, and I don't get 11.6, but that's what Maskelyne got, and that is the mountain attraction. So amazingly, even though Newton thought it was impossible, they did found an effect of the mountain's attraction. Now, I'm just going to say each side would be maybe 6 arcseconds, which is way smaller than the diameter of Mars most of the time. And that means that the mountain gravity is something like 35,000 times bigger than the mountain gravity. Or sorry, the Earth gravity is 35,000 times bigger. Then Hutton had to work out the mountain mass, and that required taking all the data points of elevation. And he made a large map, but there was so much complexity to it that he came up with a way of showing it. And he said, I'm going to connect together by a faint line the points were at the same relative altitude. He invented contour lines for land features. Now, he didn't show them in his report, and the map was the 4x4 diagram was lost. You think it would have been kept by the Royal Society, but Karen Wren, who's doing her PhD on this, made another one from the raw data. And right now she's in Ireland looking at the first site that was mapped with contour lines by the British survey. So I took a modern one, measured distances, and these are elevations in every 50 meters. So I did it all in meters. And this is a cross section of the mountain with the two sites. Notice it was steeper on the south, which is what was found. Oops, I went one too far. So you could find the mass by basically taking the density of the rock and multiply, that's about 2.5 times water, multiplying it by the volume big. But what Hutton also had to do is calculate for not only the mass, but for each part divided by the distance. Remember, the gravitational force depends on 1 over the square of the distance. So we calculated a whole bunch of vertical pillars, each with different distances, calculated it, added it all up. So Earth's gravity is 35,000 times stronger than mountain gravity. So this is the crunch calculation. The Earth gravity is proportional to the Earth volume. Remember, they knew the size of the Earth, times the mean density, that what they're trying to find, divided by the Earth radius. And the mountain gravity is just the sum of all the mass divided by the distances to the two stations. And from the ratio, Hutton was able to calculate the mean density of the Earth. And the results were, he found it was about 4.5 times water's density. Among other things, that meant that whatever is deep inside the earth must be denser than the rocks on top. So this experiment said something about it. And Halley of Comet fame thought that maybe the earth was hollow inside and it was just a shell that held together. Unfortunately, later experiments showed his result was 18% low. The accepted value is 5.5. Now, Newton, in his Principia, the English version, I have no idea if he said this in the Latin ones before. He said, however, the planets had been formed while they were yet in fluid masses, all the heavier matter subsided to the center. And my understanding, that's the current model for planet formations. They started as liquids. And it is probably that the quantity of the whole matter in the Earth may be 5 or 6 times greater than if it consisted all of water. In other words, the average of his value was more accurate than this experiment. But there's more to it yet. The calculation was redone in 1812, and the value was bumped up to about 5. Then a computer analysis took the raw data and detailed knowledge of the rocks underneath, going back for many kilometers away, using a much finer level of sections to calculate. And they, I think, went to the raw data, and they found the result from Maskelyne's astronomy data was almost bang on. So his measurements were very accurate, but the analysis of the mountain wasn't as accurate. Now, only a few decades, there was a Cavendish experiment, but I put Mitchell because he designed it and then passed away, so Cavendish finished it. How much of the accuracy and was Cavendish's careful work and how much Mitchell, I don't know. But anyway, they basically got the same 5.5 thing. Okay, I said that as soon as you have two objects with something orbiting, you can work out the relative mass. So Hutton did, he calculated from his value for Earth, different values for the solar system. And Saturn then, they could see Titan very easily. So you'd think that Saturn's would be more accurate, but it's low. And he got patterns from another French scientist, Lalande, and he predicted the values for Mercury and Venus, which don't have any moon, the moon, which they didn't know of any then, and Mars, Deimos and Phobos hadn't been discovered yet by then. So I have no idea how they got those values, but there. But there's more to it. Remember I said anything in orbit, and you know the size, you can find the mass. Well, see Ursae Majoris in fourth magnitude star in Ursa Major. Two stars were close together, and they weren't sure whether they were just happened to be in the same patch of sky or whether they were gravitationally bound. But over years, people realized that they were actually orbiting around each other, and they were able to estimate that the period was about 60 years. Then somebody did the incredibly time-consuming process of measuring the distance to it, and the modern value is 29 light years. And from that, they could weigh stars. So these experiments not only weighed the Earth, but they also weighed the planets with moons and the stars. So from that and massive double star research, they found the mass of different stars and how it works. Now, Blake is the champion of double star research in the Toronto Centre. He says you can observe them even when the moon is full. And I'm kind of hopeful because I'm plugging his passion that I might, when we get to actually be able to go to the bar again, hopefully soon, that I'm hoping for a free beer, Blake. Anyway, it also goes to our galaxy. You can't see the black hole in the center of the galaxy. invisible light, but it can be picked up in infrared, and they've been taking pictures of the black hole and various stars. And there's a star called S2 that orbits, and let's see, it's 94 on this side and 2002 on this side. So that's about a 16-year orbit. And they were able to work out the distance, and they figured out that the Milky Way black hole is about 4 million solar masses. So the same technique worked there. So what happened to the 10-foot Zenith sector? After the experiment was over, it was returned to the Royal Society, but there's no record it was sent on other expeditions. It was extremely accurate, and I think it could have done good research, especially going to a different latitude. And the British Empire, I remember there used to be maps where every part of the British Empire was red and the sun never set, but they also had colonies on almost every latitude. And it, to me, would be easy to send an astronomer who also got paid for doing a civil service job in the day to use this instrument, and maybe they could have found interesting things, very good details of that, but there's no record of it. A famous instrument asked to inspect it in 1789, no indication he used it. I contacted different museums, there's no sign of it. So I wonder where it went to. In 1821, a Royal Society committee decided to dispose of equipment. So perhaps it was bought and it's on a wall of some stately house, and maybe they don't even realize the historical importance. The other possibility to me is after the observations were done, there was a party. And Maskelyne mentioned that there was a fire in the bothy or little hut, and the fire damaged a fiddle, and he actually replaced the fiddle, and the family kept it, and this is the same fiddle that Maskelyne bought to replace, and it's in some museum. Karen Rand took that picture. I just wonder if the Zenith sector was also damaged. Maskelyne, who controlled its use, knew that and just quietly kept it there, and maybe it was such a piece of junk it was just thrown in the garbage. Sad. So, here are tools that are weighed the universe. The star of the show obviously was the Zenith sector with its careful measured angles. But they also had to use a balance that I didn't show to find the density of the rocks, the theodolite, and I argue that every astronomical measurement ended up coming from somebody that measured a length of human scale somewhere with this. So it's been a fascinating project for me to work on, and thank you for listening. I look forward to some questions.
Thank you very much, Ron. Let's go to Blake. Do we have any questions?
Yes, we do. Actually, Rhonda and I were talking about this afternoon, and she was wondering if the composition of the mountain was going to affect the results or have an impact in terms of the amount of gravitation. And I think you said that, right? That part of their work was determining the type of material that the mountain was made of, correct?
Believe it or not, I've read that the oldest rocks were at the top. So whatever process created that mountain, it completely turned it upside down. And the 2007 study had much greater knowledge of what was inside. They didn't mention that they did any drilling to a depth of, hundreds of feet or many meters. So basically they were looking at the surface rocks and took the density of 2.5. And I'm sure Chris would know more whether that's a typical value or not, but I just used the value that they said they used. But that's a good question. Who knows what was in the mountain in his day, and the error in the calculation, it looks like it came from the geological surveying side rather than the astronomical side.
Okay, very good. Yeah, we'll get Chris to weigh in on some of this, our resident geological expert. Mr. ACP 1911 says, do we know what the distance of one stadia is?
I looked into that, and believe it or not, we don't. And when I was trying to find out how the percentage accuracy of the Eratosthenes experiment, for the diameter of the Earth, or the circumference of the Earth was, and they don't know whether it was 2% or 15% because they don't exactly know what it was. So that's a good question.
Okay. All righty. I have read that the Earth accumulates material. This is a quote. An estimated 25 million micrometeoroids, large meteoroids, and random space debris enters the Earth's atmosphere each day. And this results in an estimated 15,000 tons of material entering the Earth's atmosphere every day. So, well, I've thought about this for a long time. Is the weight of the Earth changing? Is it dynamic?
There's another factor, and that is some gases escape into space. So you've got both ways. Now, I'm just doing a quick back of the envelope calculation. 15,000 tons per day is 15 million kilograms. And I think the total mass of the Earth is something like 10 to the 24th kilograms times some number I can't remember. So it's such a tiny, tiny fraction of the Earth's mass, but the Earth would have started as something smaller, and it kept, when it formed, getting hit by various large objects, including the Mars-size item that created our moon. So historically, the Earth has gained mass over the years, and my sense is if enough stuff landed on the Earth to increase its mass by 1%, you would fairly quickly have some difference to the period of the moon going around the Earth to reflect the new mass as distinct from the old mass.
Yeah, so I agree. It's not a closed loop, but it's probably very, very small, the amount that it's changing.
No, but earlier on, before the Earth cleared its orbit, which is the definition of a planet, it was getting impacted a fair amount, and it would have gained significant mass during that era.
Yeah. Okay, Lewis has a question. He said, did Hutton have assistants who did the work of the math? And if so, if he had assistants, do we know who they were?
When I read his paper, I didn't notice any mention of an assistant. But the papers are hard to read because they have, instead of S's, they use F's. You notice the section I showed, it was difficult, and I must confess I didn't read every word of the 140 pages. I would concentrate on certain parts, but I don't remember anything about having an assistant to do that. It's just a massive amount of calculations, adding up logarithms and then counting anti-logs and whatnot. It just blows me away, the effort that went through to do this experiment.
Yeah, indeed. Okay, I think that's it. Hey, thanks for mentioning double star masses. So one free beer for you.
Oh, yay! The whole thing's worthwhile. Now, I want to get together with you sooner rather than later, but we have to wait for things to settle down.
Okay, I think that's it for questions.
Thanks very much.
Thanks, Blake.